I'm Clint Greenwood with Oklahoma State University Fire Service Training, and I'm here today to take you guys through a hazmat tech refresher. Fire Service Training has been putting together several different refreshers to meet the needs of the responders in Oklahoma, and this is one of the two that we're looking at and using now. This one we're going to be looking at tank car damage assessment. Tank car damage assessment is something that's not an easy thing to do, and a lot of responders might think that's not something that they would be doing on an incident. It is. I mean, there's a lot of things that you can do before the railroad gets there, and one of those very important things is obviously tank car damage assessment. That's all part of the size-up process. So for this class, we'll talk just a little bit. Let's talk about a case study. First case study we're looking at involved a derailment many years ago, back in 1978. It happened in Waverly, Tennessee. Happened about 10:25 p.m. The temperature outside was 25 degrees Fahrenheit. There was a light snow that had been taking place. About 23 rail cars had derailed, and 2 of those were liquefied petroleum gas, LPG cars. There wasn't a release when this happened. At that point, it's just that pretty much these rail cars derailed and several of them did roll over. There was no fire, but there was some tank damage when they started looking at it. You know, one of the things, like I said, that you look at when you want to do these types of incidents, or you make these types of incidents, you want to do some type of tank assessment or risk assessment. When you do that, you can come up with your own type of sheet, if you will, to follow, or you can follow and look on the Fire Service Training website, and we'll put an example of that sheet that you can actually download and maybe use that for future occurrences. So, as I said, this incident started at 10:25 p.m. Again, nothing had been released, and when you looked at everything, everything looked fine, other than the fact that obviously we had a train derailment. When you start looking at the pressures of the tank, you start taking into consideration how much pressure is in the tank at that temperature. As with anything else, when the temperature rises, so will the pressure inside the tank. So at this time, when it was about 25 degrees outside, that tank had a certain amount of pressure in it. Now we know that liquefied petroleum gas tanks, or any type of liquefied gas rail car, is going to have what we call a pressure relief device or pressure relief valve that's going to be built into it. Well, this particular device is going to be set to open up at about 75% of the tank's test pressure. Again, where we're at now, when it's 25 degrees outside, that tank's nowhere close to that. We'd have to raise the pressure or the temperature up, which will cause the pressure to go up quite a bit for this tank. But that's with a good tank sitting up on its wheels, on its trucks, on the rail. Not one that has had all kinds of damage to it like these particular ones have had. We have 2 LPG tanks that have rolled over. They've got dents, scores, gouges. And more than likely, if there's a dent in this rail car, there's going to be cracks on the inside of this shell, which we can't see. So this is something that we have to take into consideration. Right now, time and temperature is going to be against us. If we can keep the temperature at the temperature is right now, pressure shouldn't go up anywhere. The one thing we do know about these types of rail cars is right now, at that temperature and that pressure, it's okay. It's not going to cut loose. But what happens when the temperature starts to go up? That's one of the big things we start looking at. The thing also to keep in mind is that if you start looking at a rail car and you start trying to figure out what is the pressure that the safety relief valve operates at, it's like I was saying before, it's going to be 75% of the tank test pressure. When you look at the right-hand side of the rail car, you're going to see some numbers. You'll see, for example, DOT 112J 400, and then it'll have a couple other letters. Well, that 400 is the tank test pressure. The safety relief valve is set to go off at about 75% of that. So it's going to go off for a little more than 300 PSI with that particular rail car. So as long as we don't get up to that, it's not going to open up. The problem is, with this particular rail car that's been derailed, do I have a rail car that's been so damaged that it can't handle going up that high before it actually starts to release? maybe there's so much damage to that rail car already that it's not going to be able to handle that pressure. And that's what ends up happening with this when it happened in Waverly, Tennessee. Because after about 40 hours or so, the temperature starts going up. It goes from 25 degrees up to 55 degrees. We increase 30 degrees Fahrenheit. And along with that, we end up probably pushing up that tank's pressure up over 60 PSI, causing it to overpressure and finally get to that point where there's so much damage that it has a catastrophic release. And that's what ended up happening here. Once that happened, they ended up having 16 people died, 43 people injured, and 30 plus buildings were damaged or destroyed. It took out most of the Waverly, Tennessee Fire Department. With that, several of the law enforcement, several contractors, and other people that were standing by and looking at this while this work was being going on. There was two factors that was involved when it came to Waverly. As I'd said before, you started looking at the types of things that was happening there. Are we looking at a minor insignificant incident? Yes, at 25 degrees Fahrenheit, we sure did. But as we added the heat, everything went up and became a major and a significant incident. The stress on the tank, we saw more than just one type of stress. We know we saw mechanical stress because of the derailment. We also saw some chemical that had to do with the rail or with the contents themselves, but the main thing was the thermal stress. And a lot of people, when they think thermal stress, they're thinking heat or flame impingement. Not so much the case here. We just raised the temperature 30 degrees Fahrenheit, and that was the thermal stress, and it was enough to create enough pressure to cause this tank to go ahead and release. So, in this class, what we're going to do is we're going to talk about some certain things. We're going to break down the context of damage assessment, the content, talking about inspection, the different types of damage, factors affecting severity of damage, handling damage, and then we're going to talk about how you actually apply this to the actual damage assessment. So what are the conditions of tank cars at emergencies? Well, they can either be damaged or undamaged. So it's real simple. If they're damaged, you might have an immediate release or you might not have any release whatsoever. If it's an undamaged rail car, obviously no release. The thing that we keep in mind is that punctures, ruptures, and other serious type of damage may lead to an immediate release. But then again, tank cars have sustained massive damage and there has been no release of the contents. And that's what happened in Waverly. In Waverly, Tennessee, nothing happened for over 50 hours and people started letting their guard down. That's the one thing that you need to be really, really careful about. Keep in mind that any time that we have these types of incidents, they're going to be a long-running type of incident. Don't forget about possibly making sure that you can trade out your crews. You know, the one thing that you see that happens is they start getting complacent. They've been on an incident for 4, 6, 8, 10, 12 hours, and they start to get complacent and they start getting tired. They start doing things that possibly they don't need to be doing. Maybe they might even start looking at some ways of cutting corners. So if it's at all possible, try to go ahead and make sure that you're able to trade out that personnel so that these type of things don't happen. So, conditions of a tank car at an emergency, like I said, if it's damaged, we can have an immediate release. Those are going to be the things that's going to happen. We're not going to be there for. So we'll have that immediate release that's going to take place where, you know, it's going to hopefully already run its course by the time we get there on scene. You know, some of probably our major concerns we look at is the big thing is if you've had an incident and there hasn't been a release. Why has there not been a release? Especially when you're able to look at this container and see all the damage that's taken place with this. So if there hasn't been a release, you need to start asking the question, why has that not happened? And then start thinking, okay, when can I expect that to happen? What would it cause that particular rail car to release? Going back to the Waverly incident, the one thing they keep in mind, if they had an understanding of temperature and pressure, they would understand that as the temperature went up, the pressure goes up in the rail car. I've already have a damaged rail car that's not going to be able to handle a higher pressure. Maybe they can't do anything for the rail car, but maybe they can go ahead and make sure they isolate and evacuate the area, and that way they can keep people from getting injured. You're going to impact and save more people's lives through proper isolation and evacuation on your hazmat scenes. Maybe this rail car has been subjected to an additional stress. You know, is it Did it have thermal, or is it mechanical, or is it chemical types of stress? What has been put in that has caused that to happen? If you don't have a release, keep in mind it could be a delayed release. So then I want to know, is it going to be a violent or a non-violent release? Again, that's going to be a big deal. If I'm going to have something that's going to release like a BLEVE, boiling liquid expanding vapor explosion, we're talking something that's an explosion, a detonation faster than the speed of sound. Or I could have something like a violent tank rupture that's going to be a little bit less. A lot of people will kind of downplay a violent tank rupture, which is not a BLEVE because it's subsonic when it comes to speed. But I still wouldn't want to be standing next to it when it did that. So keep in mind, you know, if you're going to have a release, anything that's going to release from the container and reach out and touch you, it's not going to be good for us. So we want to isolate and evacuate appropriately. Delayed releases, like I said, are very, very dangerous due to the potential responder involvement in response or wreck clearing operations. It doesn't have a release. We get up close and personal to these incidents, and then that decides it wants to go ahead and release it. That's where it can do it. It will lull us into that false sense of security, thinking, well, if it was going to release, it's going to already have done it. That's not necessarily true. There could be one little thing that's holding it back, and it's waiting for some small change. Again, something as small as a temperature increase could cause this container to go ahead and release everything. They had delayed releases in a lot of the major BLEVEs that you see throughout the United States that have happened in hazmat history, if you will. Kingman, Arizona was a delayed. Waverly, Tie Siding, Wyoming was a delayed release. So was Crestwell, Delaware, and Hemsdale, North Dakota. There's lots and lots of examples, if you'll see throughout. When you look at this slide, you can see several different types of places that's had some sort of chemical release after a train derailment. So what's our job? Keep in mind, guys, your job is to favorably change or influence the outcome of the incident. We want it to be a favorable change. We don't want to become part of the problem. We don't want to bring victims, if you will, to that incident. How do I do this? Well, first thing is I got to start looking at this four-step process. I want to be able to analyze the incident, do a proper analysis of what's going on, a size up of it. From that size up, come up with a plan, a game plan on how you want to handle the situation. Dot the I's, cross the T's, think it through. You've got time. Once you got that plan and everybody's on the same sheet of music, implement the plan. Follow it to the letter, make changes as needed, and move forward. As you've put and implemented that plan, don't forget to evaluate it. Because once you evaluate it, it becomes a cyclic type of problem. You're evaluate it, you're going to analyze what you came up with, and it's going to go again in one big circle, and you're going to continue with the whole process throughout the incident until you terminate the incident. Beener said, estimating likely harm without intervention is one of the things we want to do. So that was Ludwig Beener from the National Transportation Safety Board back in the 1970s. He came up with the way of doing an analysis. He wanted to figure out, how do most hazmat incidents work? And essentially he followed this flow chart, if you see right here. He would first and foremost determine if there was a hazardous material involved. If he indeed figured that out, we know that we're going to go ahead and initiate the incident command system. We want to initiate command and control. Then you start looking at the data collection side of the incident. You're going to survey that incident. You're going to inventory the incident, however you want to call it, but you're going to look at that incident and figure out what you've got. You're going to collect and interpret your hazard response information, and then don't forget, you've also got to look at those containers. You want to assess damage to the tank and its fittings. And then once you've got that data collection, you start doing the data processing. You're going to start predicting the behavior of that container and its contents, and then estimate the outcome. So what's likely to happen? In this class, what we want to be able to do is, given an incident involving tank cars, we want to be able to identify the significant tank car damage. We want to look at the type of damage that's taken place. We want to look at the factors that affect the severity of the damage to the container. We want to look at the stress that's been put on the tank. We want to assess potential for delayed tank failure. And then we also want to describe the risk-based action options using facts, science, and circumstance for this incident. When you look at the General Hazardous Materials Behavior Model, GIMBRO, When you look at that, it is broken down into a sequence of events as follows. First off, we look at the stress on the container. That's the first thing we're looking at. What kind of stress are we looking at? When we notice this and we look through these steps, we find out the one thing that as we go through those steps, the likely outcome is the next step. For example, if I put a certain type of stress and I overwhelm that container, it's going to breach. Then I've got to figure out what kind of breach I'm looking at. And that's going to have a lot to do with the type of container that I've got. When it starts to breach or I have a breach, we're going to get a release. And then it's going to engulf, it's going to make contact, and then it's going to have certain hazards that are going to happen to us. When you look at engulf, contact, and hazards, that's the behavior of the contents that's being released. So we start off again when we're predicting behavior, we start with stress. Something happens to a container before the contents are released, both damage stress or both to weaken that tank. That can be thermal, whether it's hot or cold. It can be mechanical, it can be chemical. When we start looking at things like radiation and etiological, that's a type of energy transfer that takes place. But those first three are the ones we really look at: thermal, mechanical, and chemical. So after that stress, once it is pushed that container beyond its limits, we're going to get a breach. And that's what we're looking at. Once stress beyond recoverable limits, a container loses its ability to hold the contents and opens up, again, a breach. This can be like through a disintegration, runaway cracking, attachments, closures open up. In other words, we're talking like pipes and fittings are broken off or snapped off, punctures, and splits or tears. Once we have that breach, we move into what we call release. When a container fails, it breaches, its contents may be released. All the stored energy that's inside of the container, it's going to come out and speed that release. It's going to push out. You know, we're looking at a detonation faster than the speed of sound. A violent rupture, a little bit slower than that. Rapid relief could be minutes, hours, and days. A spill or leak could be minutes, hours, or days as well. This is all according to the speed of the release. Again, when you look at this type of release, for example here, the picture from Kingman, Arizona, this is a violent rupture, okay? This would be a Blevy. Whereas you can look at the next ones from Castleton and Texarkana, those are heat-induced tears that take place. The difference between the Kingman, Arizona and Castleton and Texarkana is Kingman is a result from a liquefied gas container, so I'm looking at more of a Blevy type of release. Whereas Castleton and Texarkana are from liquid containers. So I'm looking at, could be oil or gasoline or something like that. These are atmospheric pressure containers. So that's where I get that heat-induced tear. So what's likely to happen? Again, looking at that picture, I go back, I look at the product. The product is ethylene oxide. I know it's a liquefied gas. I look at the type of tank that I've got. This is a liquefied gas. It's going to be in a pressure container, okay? What kind of damage? I can see on this container, I've got mechanical damage. I've got huge dents. I probably got scores on the inside of that dent. Is probably cracked. Again, so it's a really, the container is thinned. It's only as strong as the thinnest part of the container now. How severe is it? This is significant. This is a significant damage to this rail car. What kind of stress? Like we said, it's mechanical. The potential for delayed release, obviously, because it is not released yet, it's already delayed. Delay can be 5 minutes, 10 minutes, 2 hours, 10 days. If it doesn't release on that immediate deal, I'm looking at a delayed release. We still do not want to get complacent and forget that this could release on us. And then what kind of breach can I have? What kind of release? Well, this one, it could be any number of ones. We can have from very small to a rapid release to a runaway crack to, again, to something like a Blevy. On this next video, you'll see what happens and what kind of damage these rail cars can actually take. This is a tornado actually hitting the backside of a train. This camera is showing from the back of the locomotive. So then you see what happens when the tornado goes ahead and takes care of these things. Again, that could end up in being a delayed release on that particular incident. The next thing we look at, again, staying with this assessment and for the tank car damage. You know, doing tank assessment or assessment for this, what does this do for us? Well, first off, it benefits us. It gives us a better understanding of what we've got as far as the type of damage. You wouldn't go walk up to a structure fire and not do some sort of size up. It's the same thing on hazmat calls. You need to be able to go forward and do a size up for these. It helps you protect yourself as well as others. Again, you will be able to look at this incident and realize, hey, this is something that can get bad really, really quick. I need to be able to isolate and evacuate the people around here. As I said before, you're going to save more lives and protect more persons by proper isolation and evacuation. Using your emergency response guidebook would be key for that. Keep in mind that that guidebook is good for that first 30 minutes of an incident. It'll help you understand the problem. In other words, this is what I'm facing, this is what I got to be able to handle. This is all part of that analysis step I talked about earlier. You plan your response. I analyze it, I come up with a plan, I know how I'm going to handle the situation. It'll help me handle damaged tank cars without tank failure as well. I can be able to start identifying which ones are the ones that are more than likely to go bad on me. When you're doing assessing of this type of deal, there's some things we want to make sure we look at. First and foremost, we'll look at the inspection process. We look at the types of tank damage, the factors affecting the severity of this rail car, handling damaged tank cars, and then the whole application of the situation. When you're looking at inspecting it, the preparation or the basics is probably one of the most important things here. We want to be able to identify the type of cars that are involved. If I can identify the types of cars, I can tell you more than likely what's the physical state of the product in there. I need to know, is this a liquefied gas? Is this an atmospheric type? Or is this something that maybe is holding a solid? That helps me a lot when I have to figure out how I'm going to handle the situation. Should be able to review construction, fittings, and likely behavior of those cars. I should know how a liquefied gas car is going to react. I should know how a liquid car or a solid. I want to be able to identify the orientation of each tank car. In other words, how is it laying after the derailment? Is the safety relief valves underneath the liquid? Yes or no? I mean, that's a very, very important thing for us to know. If it's below the liquid line, it's going to have a tough time relieving any kind of pressure because those valves are not made to relieve pressure of a liquid. It's made of a vapor, and a gas is what's supposed to come out of those valves. Some basic safety precautions. Obviously, we want to control access. You don't need 5, 6, 7, 8 guys down there looking at certain areas. You might want to divide up if you have a large derailment area and sector everything off, create divisions some way, but you don't need to have a whole bunch of people down there looking at the same thing. Look at the buddy system, don't forget about 2 in, 2 out, and then just work your way through there and be systematic about what you're doing. When you're doing a damage assessment, it's not something that goes fast. It's going to take just a little bit to look at it. Keep in mind, you're only going to be able to look at so much of the rail cars. You don't need to be climbing around on top of the rail cars when you're doing damage assessment either. We want to try to do all of this from the ground level. There's no reason to be up on top of this. We don't know if it's been secured. We don't know if it's going to rotate or do anything like that. We don't know the stability of the rail cars. So again, we're doing everything from the ground level, and we're trying to do it, make sure that we're not up underneath anything that can fall on us as well. We want to control ignition sources. You think about that, that's something that people take for granted. But again, we can actually bring in our own ignition sources. It could be something as simple as static electricity. So we want to be real careful what we're doing there. Use your appropriate personal protective equipment, when you're doing inspection, especially because you're going to be up close and personal a lot of times. Don't forget that direct reading instruments, monitors, are also part of your personal protective equipment. You should not be sending in any team in without any type of monitors that can go in there. If you have the access to the consist or the train log, if you have that ability to get that information, you should be able to tell what type of products you might be up against and help you better find the product. It's always a good idea to be able to get that information straight from the railroad. They should be able to email you that and give you the most up-to-date one. It's been found that some responders will get in trouble. They get the one that maybe is carried on the train itself. Well, that train could actually be, that list could actually been changed in the last 3 or 4 or 5 hours. And it might have you looking for a rail car that's no longer there. or a rail car has been added and if for whatever reason it's not being shown on there. So get in touch with the railroad to get the most up-to-date that you can of that. Well, again, we want to look at, we got to be able to determine it's safe. We need to know what the internal pressure is for this particular rail car. And I know that most of the hazmat teams out there don't have a gauge that they can put on a rail car to find out what the internal pressure is. So what we're going to have to do is kind of do a little rule of thumb. So when we look at that, we find out what the vapor pressure of the product is. And let's just use propane. Propane at 68 degrees is about 123 psi, okay? When I'm looking at that, I want to keep that in mind. So when I look at a rail car and I see it, I can say, hey, the pressure inside of that at 68 degrees outside, it's going to be 123 psi. But what is it when it is 78 degrees outside? Well, that's where we keep in mind that little bit of rule of thumb. For every 1 degree increase or decrease, there's a corresponding 2 psi. So if I'm saying that, hey, it's 78 degrees, the difference between 78 and 68 is 10. I multiply that times 2, that makes 20. I add that to my number that I said earlier of 123 psi. So at 78 degrees, I can expect about 143 psi in that liquefied petroleum gas rail car. And it's just, again, a rule of thumb. That's going to get us somewhere in the ballpark. Remember then, when I've got that pressure in my mind and I'm working through it, don't forget about what I said when we talked about the test pressure, and the safety relief valve is set to go off at 75% of that. So that can kind of give you an idea of where you're working at. The problem is when you look at that, is you can't tell how strong that rail car is once it's been damaged. You start looking at the damage assessment, and if something looks really bad to you, and I like to say is it looks really ugly, you need to make that mark. And you need to, don't keep that to yourself if you're the team that's doing the assessment. Let command know that you've got a car that you think this is going to be significant, and this is something we need to start planning for to keep away from. Isolate that. Work out what the product is. Is this a liquefied gas? Is this just a straight liquid? Is this a solid? Whatever this is, and take the appropriate measures for that particular rail car. Try to figure out how much product's in the container if that's at all possible. If there has not been a release, you should be able to get that information readily available. If it's been released, again, if it's going to be a liquefied gas, you're not going to be up and around that trying to figure out what that is. But if you do have a liquid that's being released, that might be something that you'll be looking into. So the actions that you can perform when it's safe: inspect all the accessible surface areas when you're looking at that rail car. Re-examine the adjacent cars or the tank itself when it's moved. Examine all the damage carefully for the factors that affect the severity. We want to be able to look at this container and look as much of it as we can. It's usually those parts of the rail car you can't see is where the bad damage usually is. Think about this. You're going to see some stuff that's going to be damaged, but what is it laying on top of? That can be where the significant damage is and we might be missing. Having a tank car damage assessment sheet like the one that we're going to provide on the website, it'll be very helpful for you, or you can create one of your own. I think this is a good one that we received from some classes we've done years ago. And it's just a good starting point to kind of help walk you through that if you're doing damage assessment or if you haven't done a damage assessment in quite a while. Some of the conditions that we want to preclude inspection: direct flame impingement on the vapor space. I don't need to be up there doing inspection that way. The tank is in a pool of fire. Don't need to be up there doing that. We know that the problem is we've got, on both of those, we've got some type of flame impingement. Maybe the pressure relief device is operating. It's increasing in pitch, increasing in flame height. That's probably something we're going to need to back off from. And don't forget the visible bulging of the tank. If the pressure's going up in the tank and it's enough to make those sidewalls move, we need to move out. We need to get away. Isolate and evacuate the area as fast as possible. If there's any other conditions that just don't seem right to you, go ahead and isolate and evacuate the area. Remember, we're not bringing victims to this incident. We don't want to be part of the problem. If you don't really understand or you don't know, back up. Again, the best thing you do, isolate, evacuate. Get a call into the responsible party, the railroad, and let them know what you've done to that point. Be ready to establish a unified command with the railroad as well. So again, looking at this type of damage, tank car damage assessment sheet, Again, you should be able to take this and work your way through it. You'll be able to identify the type of damage, the factors affecting the severity of the damage, and then also figure out the type of stress to the rail car. So what are we looking at here? Well, this is this airplane back in Aerospace America, they call it the Comet. And this particular airplane, they actually found that it had some flaws in it. And they call the type of stress that took place to this type of the metal that was used to make this airplane. And essentially it ended up creating types of cracks in there. And when it did, they found out that it created those types of cracks. It caused it where it was a weak spot. If you ever try to open up a bag of peanuts, or for me, I always said one of those ketchup or mustard packages, and you sit and you mess with it, and it just seems like you can't rip it, but you got to get it just right. Maybe you get it started, and then it just opens up really fast. Well, think of that kind of the same thing that was happening here. Is once it finally found and got a little nick, and if you can see the picture that's been circled here, they kind of look at that little nick in that metal. That's what created the crack there. And it took you to get to that little nick to get that started. If you can't get that started, it's real difficult to pull that apart, and it seemed like it'd be really, really strong. But that's one of the things that we look at that we don't think about when it comes to metal. It's all about that little beginning part, that little nick, if you will, that creates the crack that causes the release to start. So what type of notches are we looking for? Well, we look at them for the cracks. We look at them at dents, rail burns, metal thinning. We look at scores, gouges, wheel burns, flame impingement, and corrosion. Anything that causes a thinning in the material is something that we're looking for the type of damage. Again, when you look at dents, scores, and gouges, these are things that create that type of deal. Again, we go back to that little piece that we can take and rip that out. Another thing that you can find, you can download was it's for this call it the paper exercise. And what it does is kind of drive the point home about dents, scores, and gouges and cracks when it comes to the base metal on a rail car. So you'll see if you look at the sheet that we're going to put up here on the screen, you can actually download this, and you can make enough for your guys, and you guys can go ahead and do it and also show them that. But what we want to do is we want every person to have 4 pieces of paper. So I've got mine. I got 1, 2, 3, and 4. And what we want them to do is when you do yours, as you can see on this slide here, is that one of them, I don't want anything done to it. I just want a blank piece of paper. I don't want any cuts, so just a square piece. I took an 8.5 by 11 sheet of paper, and I folded it in half twice, and then I cut it out, so I'll do that. And you can see on the slide, you can see where there's 2 X's. Well, that's where I want you to put your fingers. And essentially what I want you to do is take your fingers and hold on to the piece of paper like this and just pull. And just pull straight away. Don't twist it or anything like that. I want you to create pressure. And notice how much pressure that's going to be able to handle that. Think about it this way, is that think of that as the pressure on the inside of the container, and it's pushing on that. It's able to do that. Now, I'm sure there's some big, strong firefighters out there. They're going to be able to rip this thing in half. But if you kind of follow the exercise like I'm showing, you can see I'm putting this under stress and pulling it. It's not going to tear, okay? So that one held up pretty good. The next one, what I want you to do is I want you to just put a little bit of a cut in it, like this one. You can see how far down I did it, not quite a fourth of the way down. And the same thing as I want you to put your fingers on these 2 corners and just go ahead and try to pull it straight, and you notice what's happening there. See the pressure that's taking place? I'm slowly doing this, and it's not taking much, a little bit more. And yeah, sure, it's going to tear real easy. You notice that. Because it was that little piece, that little notch that was in that metal, if you will, that gave it that opportunity to go ahead and tear a lot easier. So we can do another thing here is take the next one and do the same thing here, but you see how I kind of cut out kind of a bowl, almost like a dent? Same deal, guys. You'll notice if you look at it, I pull it and you can see it starting to pull apart. Notice the bottom of that bowl and what's happening there. And before long, it goes ahead and rips apart. Took a little bit, didn't take quite as much for it to tear as it did on the one with just the slit. And then the last one, we're just going to cut a V, but look at this. I'm barely even pulling. You can already see it already starting to try to come apart because this has become the weakest. Think of it this way. This is now that deepest dent It's a sharper dent, if you will, in that side of that container. And you can see it's not taking much anything. It's wanting to just rip. I can't even hardly keep it together. I go back to this again. This is the one that didn't have anything in here. And I'm giving it a little bit of pull. I'm even yanking on that a little bit, and it's still not going to go ahead and rip. So think about that as it is when it comes to the tank itself, when it comes to the damage that takes place there. A crack, when you're looking at the cracks in these containers, that's going to be a narrow split or break in the tank material. Typically, it's found in tension areas. It can grow at the speed of sound under pressure, and critical when associated with any other type of damage. So if I got a dent, you're going to probably have a crack that's going to be in there as well. They're not always visible, like I said, but there might be some frosting or clear liquid or dye penetrant that's coming out of this container, depending upon what type of product's inside. If you got a crack that runs longitudinal, that's more severe than running around it crack. So if it runs the length of that rail car, it's going to be a bigger problem than it would if it kind of goes up and around on it. Cracks that go through the fillet wells, that's another problem that we have to worry about because it's actually starting to take away from that strength. If you've got a dent, like for example in these pictures here, I got an abrupt change in the tank's contour caused by impact with a relatively blunt object. These dents, when you go back and you look at these, you can see what happens again, as I mentioned earlier, is when we push into that container, we're actually taking away from the expansion space in this on this particular type of product. This one being a liquefied gas on both of these pictures. Some concerns we have when it comes to dents, if you combine it with a crack or another damage, it can be a real problem. If I've got a dent across the heat effective zone, that's the area on the either side of where the welds take place. If you've got a sharp radius or curvature of a dent, the sharper, as I said earlier, the sharper the dent, the worse it is. The more chances there's going to be cracks on the inside of that. Dents decreasing volume or decrease in outage decreases time until failure. So like I said earlier, I got bigger dent, I don't have as much up there above in the vapor space or the outage, it's going to cause it to possibly fail a lot sooner. Dents, you look at that, you can't always see what's going on there. For example, on these pictures, I look at the outside of this dent. This is kind of shown on the inside, but when we look even closer, we can actually see there's a separation of the tank and the weld itself. So again, this tank's only as strong as that point right there. We can have rail burn. That's a long dent in the tank metal with a gouge at the base of the dent. The problem that we worry about when it comes to rail cars is if these things are over 7 foot in length, it can be a real problem for the rail car. If it goes across the heat effective zone, if along with the metal removed, it's gouged out. So again, you gouge out metal, we're thinning the wall of that tank. Scores or gouges, again, anything that's going to be removing of the tank or weld metal along the track of the contact with another object. So again, chiseling this out, if you will, it's removing the strength of this container. Sometimes it's real difficult to see. For example, in this picture here, we're looking at the inside of a jacket, and you can see the base metal has actually got a score and or gouge here. Being able to tell how much metal's been removed is real important. Looking at this one, it's very difficult to be able to do that. Here's an example of wheel burn. What happens here is, in actuality, is that the train or the rail car comes up off of its trucks and then it lands back down on the wheels and it rubs on top of those. And that's what took place here. You can see how it ground it down on the outside, but you can see the damage that started to begin on the inside of this container as well. This is an example of how they could go about it. I see this is high-tech technology here on how to figure out the depth of metal that's been removed. But hey, whatever works here. Essentially laying a stick or something across there and then measuring down and then finding out how long or how much of that's very important. I mean, you're looking at this could be up to 1/4 to 1/2 inch of metal that's been removed from this particular tank itself. Flame impingement, another one. We all know what it comes when we talk about flame impingement. Where's the liquid level? How much product's there? Is it up in the vapor space? That type of deal. Is the container bulging? Are we seeing any pressure? Is the safety relief valve open? There's so many things when it comes to flame impingement that we pay close attention to. What is the product? Is it flammable? Corrosion's another thing we often will forget, but there's times when you'll have a container that just does not get along with the contents. Maybe we put the wrong contents in it or something. There's been noted of times where a rail car actually came apart, like on this one in Selkirk, New York, back in 1996. This rail car actually came apart, split apart, and shot down the rail track. So when we're assessing tank car damage, the first thing we're looking at, as I said, let's look at stress. What type of stress do I got? Is it thermal? Is it going to be mechanical? Or is it some type of chemical stress? Then what is it that's affecting it? What are the factors affecting the severity of this rail car? What type of metal properties do we have, or are we working with this rail car? Has it damaged the heat effective zone? Yes or no? How about how much metal's been removed? Has it been graded off, gouged off, what? I look at the dents. How sharp is the radius of the dent? How long is the rail burn? And then where's the liquid level? The type of damage, is it a crack, dents, rail burns, so on? Metal thinning, scores, gouges, wheel burns, flame impingement, and corrosion. Factors affecting the severity. I looked at the metal itself. What's the ductility of this? How tough is this metal? Does it do good in cold temperatures? Yes or no? What's the high ultimate strength of this particular metal? Remember the Titanic. If a tank is, when we talk about it, what were some of the factors that caused it to sink? Obviously this thing, it had scores, dents, and gouges, and it also was punctured one way or another. If the tank is warm to the touch, metal will be ductile. Cold work reduces the ductility of the metal. So in other words, the cooler it is or the colder it is, it's not nearly as pliable. It can be brittle. Understanding when this metal was made, this isn't getting to be as much of a problem anymore, because most of the metals that we're seeing out there in most of the tanks in hazmat, they're a lot newer than 1988. So everything that's actually been made after 1988 is heated and been able to handle up to for an hour and then cooled. This allows that metal to be a little more ductile. How does cold work come into play? Is it brittle or not? In the Minot incident, they had over 146,000 gallons that were released from a violent rupture in 5 rail cars. 74,000 gallons from 6 other cars, 1 fatality, 10 serious injuries, 322 minor injuries, $2 million in damage, and $8 million in cleanup. The steel issue is one of the things they looked at was it made to be able to handle this type of incident? So the next thing we're looking at is public protection when it comes to handling these damaged tank cars. Control access to the endangered area, obviously. We've talked about that quite a bit. Isolation, evacuation, evacuate or protect in place depending upon the situation, depending upon the product, and also obviously depending upon what's in the path of that. You have to take into consideration, it could be something like a nursing home, it could be a detention facility, it could be schools, whatever the factor is, you got to look at that and take that into consideration to figure out whether or not you're going to evacuate or shelter in place. Take appropriate action based on the available resources you've got in your current technology. If you don't have the ability to handle those, don't try to do something that you're not equipped to handle. Use your lifelines, people that you can talk to. Shippers, carriers, BOE inspectors, tank builders, repair specialists, it could be response contractors, and then networking contracts are all people that you can use to get a hold of. When you're looking at the different problems that can happen, whether you got a leaking fitting, overloaded tank or car structure damage, there's things that you can do and ways that you can figure out to handle that situation. Look at the things that you're able to do, what actions you're able to complete with your department. You might not be able to do all of these things that we're seeing right here. For example, maybe you don't have the ability to transfer product or flare or vent a product. If you don't have that ability, again, you go back to the things that you can do. Isolation, evacuation is the one that we've hit really hard with today. So when we look at pressure tank cars, for example, we have those options that we can do. For example, maybe we can reduce the internal pressure, or maybe there's no tank movement, unload, or transfer that can take place. Maybe we can look at uprighting, unloading, or transfer. Maybe they can be re-railed, moved a short distance, and unloaded somewhere else. These are all options, But again, keep in mind, these are options that will be discussed with the railroad. So if you have a pressure rail car, how are we going to handle that? You got several things that are going to take place or happen with that rail car. You're going to have damage to the hazmat itself. Maybe you look at the rail car and it's got visible cracks, or there's some type of dent that's damaged it. It's got a lot of rail burn, a wheel burn more than a 1/4 inch deep. You see scores and gouges. How do I handle those situations? Maybe I still got a safe pressure, maybe I don't. Being able to reduce that internal pressure is very important. Can I do that? If I can't, again, I only go with what I can do. Can we unload, transfer without moving the tank? Again, that's something that we'd be looking at and working through with the railroad. You look at the wheel burns, anywhere from 1/8 to 1/4 inch deep. They're probably going to look at uprighting it or unloading it or transferring the product. If they've got an undamaged dent, wheel burn up to 1/8 deep, they might just re-rail it and move it a short distance and then offload it. So again, these are all things that could be happening with the railroad. I urge you again to get with the railroad and find out what the game plan is. This is going to be unified command. You're going to work together with them. So as you go and do that, keep in mind, look at your inspection procedures, look at the type of tanks and the damage that happened with that tank. What are the factors affecting severity, and then handling the damaged tank cars? How are you going to go about doing that? So when we want to do the damage assessment, looking at this particular rail car right here, okay, what's the product? I'm looking at it and I'm seeing some names on here, and I look down there in that lower right hand side, I can kind of make out what it says. Looks like it might be ethylene oxide, and I can read something that says inhalation hazard. What kind of tank is this? Well, I look at the type of tank it is. If I'm not sure, maybe I can use my emergency response guidebook and I can look through it. But looking at that one with the protective housing up on the top, I'm going to lean toward a pressure container. What kind of damage? Oh, I'm going to say I got dents, scores, gouges. I got cracks in this particular one. How severe? Very severe. This is going to be up there at the top. A lot of mechanical stress that's taking place here. Is there potential for delayed release? Of course. I don't see it releasing now. It's going to be a delayed release. What type of release? It can be the really, really small, or it could be a levy, depending upon what type of energy I'm able to put toward this to cause a release. So again, there's ethylene oxide, like I said. Looking at this particular tank, this one's hard to see. We look at that product there. It's really difficult to tell what it is, but it's something that's burning off of there. We look at that product and see it's white phosphorus. Again, you start looking at the tank. The problem is, when we see this type of deal going on there, would we be up there doing any kind of damage assessment? No. I'd be doing the damage assessment with a pair of binoculars from a distance. This isn't something I'd be looking at. What would I be worried about? How about the rail cars that are right there in that area? What's close to it? Is there something I can figure out that we've got? Again, keep in mind that these exposures, it might be this white phosphorus that's burning here that might be all it needs to create a chain reaction and work through the rest of this derailment. Here's Kingman, Arizona. Well, that type of product, remember we go back at LPG. Type of tank, going to be a pressure tank. What kind of damage? Hard to tell from here. But again, this could have been something that had to do with the valves being ripped off or something along those lines, attachments, and caused a leak, and it finally went ahead and lit off. We've got some mechanical damage. We've got thermal damage, or mechanical, thermal damage. We've got pretty significant, pretty severe. We've got thermal stress. What's the potential for the delayed release? It's releasing now, but can it get worse? Yes or no? And there's a good possibility. As we know, this thing would end up levying. This is a Texarkana. What type of product do I got? I got propylene. Looking at propylene and finding out what kind of product this is. The type of tank here, figuring that out. By looking at this picture, it looks like a lot of things have already happened. It's already released. It was a pretty severe damage and severe release. What's the likelihood of something else happening? Well, those are some things I look at. Think outside the box a little bit here and figure out, is there something else there that can hurt me or harm me? What needs to be done? This might be that possibility we just let it sit there and burn itself out. But remember, as I said on the other incident, is there something here that could be an exposure that this could be a catalyst to and cause it to take off in a chain reaction? Here's chlorine. When we look at the chlorine rail cars, we start worrying about all kinds of things. We know what chlorine is. It's going to be in a pressure tank. It looks like I've got a score here. When we look at that score, I know the thing is that I've been removing the metal from this container. What are the types of things I need to be worrying about and thinking about there? If this was all part of a derailment, is there any other damage that's taking place here? These are all things I want to take into consideration as I work down my damage assessment. Here's styrene. This is styrene monomer. This is a product that is a non-pressure container, but it looks like it had some pressure behind it. Understanding what styrene is, being a monomer or polymer, this is something that we know that can actually overpressure, and that's what happened here. Is this thing done, it's overpressuring, or is this going to just the beginning of it? Can I expect a catastrophic failure of this tank, yes or no? The one thing with polymers is once they started, they're not going to end until they're done. There's nothing we can do to stop these from having that reaction. And then the last one here, the bacon crude oil. When we look at it, again, we talk about a liquid that's in an atmospheric container. Burning here, this is when we look at the types of incidents that happen with these types of deal, we can look at the type of damage. Obviously, we've got some kind of mechanical damage and now thermal damage. Pretty severe thermal mechanical stresses. Potential for delayed release, yeah, but in the other cars. The heat and the flame can be heating up the other cars and causing them to have some sort of release. So, as you can see from all of the other those scenarios that we just kind of ran through, there's more than just worrying about the container that was the object that we looked at with the damage assessment. They can impact everything when it comes to the derailment. Before I go any further, one thing I want to do is I wanted to acknowledge Charlie Wright. Charles Wright is very instrumental in this program. This is something that I was actually got to sit with through his program several times, and very instrumental in helping us get this type of information together in this subject matter. If you got any questions concerning this information or anything else along these lines as far as hazardous materials, you can contact John Carpenter up at OSU Fire Service Training. He'd be more than happy to help you out. And until next time, you guys be careful. Thank you.